Hi, in today's video I'll be looking at calculations for AS Chemistry Unit 1, and specifically I'll be covering 1.3 subsection of the Edexcel specification. So here is the specification points that I will be looking at today. This is taken from page 25. So we'll look at some definitions which we need to know, and then we'll also learn how to calculate number of moles, the molar mass, and when we're dealing with volumes of gases and so on. We will also look at percentage yield and atom economies. I'll also mention the Avogadro constant. I just wanted to mention this book, which was recommended to me by my friend. It's called Calculations in AS and A-Level Chemistry, and it's by Jim Clark. I definitely recommend that you get it. You can get it from your library or from Amazon. There's quite good deals on secondhand books, because it is very, very clear, unambiguous, and he explains everything in very good detail, and also gives you a lot of worked examples before you sort of attempt to do the questions yourself. So definitely recommend that, because before I found this book I was really struggling with calculations, but this definitely helped. So the key definitions that we need to know are shown here. I won't go into the first three because we've already discussed those in a previous video, but the things that are new are the three last definitions, which is the relative atomic mass, which is the average mass of the atoms of that element, which relative to 1/12 the mass of a carbon-12 atom. Also, relative isotopic mass is the mass of one isotope relative to 1/12 the mass of a carbon-12 atom. And relative molecular mass, which is the sum of all the relative atomic masses of its constituent atoms. Three different types of formulae that we need to know. So the molecular formula it shows the number of atoms of each element in one molecule of that substance. So for example, the molecular formula for glucose is C6H12O6. Therefore, each molecule of glucose contains 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. So that's the molecular formula. Then we have molar mass, which is the mass of 1 mole of the substance, and the units are grams per mole, as shown here. So the value of the molar mass is found by adding the relative atomic masses of all the atoms present in the formula. So, and you can find the relative atomic masses from the periodic table. So for example, if we looked at the periodic table at carbon, we can then find out that the relative atomic mass of carbon is 12.0. So we can use that in our calculation. So for example, the molar mass of glucose, we know that the relative atomic mass of carbon is 12, and we have 6 carbons, therefore we multiply it by 6. We have 12 hydrogens, and the relative atomic mass of hydrogen is 1, so we multiply it by 12. And the relative atomic mass of oxygen is 16, and we have 6 atoms of oxygen, so we multiply that. And when we add all of these together, we get the molar mass. So the molar mass of glucose is 180 grams per mole. And finally, we've got the empirical formula, which is the simplest whole number ratio of the atoms of each element in the substance. So for glucose, it will be CH2O. And that's because if we look at the molecular formula, we can see that we have 12 hydrogens and 6 both of the oxygen and the carbon. So we can divide all of these numbers by 6, meaning that we have only 1 carbon left. 12 divided by 6 gives us 2 hydrogens and 1 oxygen. So that's the empirical formula. Okay, so let's look at how we calculate empirical formula. And this question is taken from page 44 of George Face's AS Chemistry book, specifically designed for Edexcel. So this question gives us a compound, and it tells us what atoms are present in the compound, and it gives us the percentage of each. So the easiest way to do this calculation is to draw yourself a little table, like shown here, where first of all you write out each element that we're given. So we're given sodium, carbon, and oxygen. We write all the elements down. We're also given the percentage. So in the next column, I've already pre-written the percentages. The next stage is to divide the percentage by the relative atomic mass, which, as I said, we can get from the periodic table. So for sodium, we divide 34.3, and we look at the periodic table for group 1 for sodium, and we get told that it is 23. So once we divide that, we get 1.49. We do the same, so we've got 17.9% of carbon. The RAM of carbon is 12, so we divide that by 12, and we get also 1.49. And we do the same for oxygen, so we've got 47.8%. We divide that by 16, and we get 2.99. So in the next column, we have to divide whatever number we got in the previous column by the smallest. So the smallest number is 149. Therefore, we divide each number by 149. So if we divide this, we get 1, and the same here. And if we divide 299 by 149, we get 2. So this is our ratio. We've got 1, 1, 2. So then we can work out the empirical formula. So we know that for sodium there is 1 of it. So we just write sodium. We don't usually write 1. For carbon there is also 1. So we write C as 1. And for oxygen we got 2. So this is our formula of our compound. And this is the easiest way to work it out. So let's look at another example. So let's follow the table through again, like we did in the previous. So we've got calcium, phosphorus, and oxygen, and we get given the percentages here. So first we need to divide each percentage by the RAM. So 38.7% divided by the RAM of calcium, which is in group 2, is 40. So we get 0.97. Divide 20% by phosphorus, which is 31. We get 0.65. And 41.3 divided by 16, we get 2.58. So we now need to, so we've got 0.97, 0.65, and 2.58. So obviously the smallest number is this one. So we need to divide each of these numbers by the smallest. So the first one, we get 1.5. For the next one we get 1, and for this one we get 4. So this is the ratio. We get 1.5, but they have to be whole numbers. So in order to get rid of this 1.5, we need to multiply everything by 2. So we need to multiply this to get rid of the 1.5 to make it a whole number. So in that case we get 3, 2, and 8. So that means that the empirical formula is, we've got calcium, and the ratio is 3, so we write there's 3 of calcium. For phosphorus, we have 2, and for oxygen, we have 8. So that's the empirical formula. So now that we've worked out the empirical formula, we are also asked, as part B of the question, we asked to calculate the molecular formula. So we've got calcium times 3, so we need to multiply 40.1 times 3, plus we got 2 of phosphorus, so we need 31 times 2, and we have 8 of oxygen, so 16 times 8. So the total comes to 310.3. So because this number and this number are very similar, I think if we did the calculation with more precise values here, probably get 310. So it's numerically the same as the molar mass of 310. Therefore, the molecular formula is also Ca3P2O8. So amount of substance, it can refer to grams, which we use to measure mass. So 1 gram contains 1,000 milligrams, and 1 kilogram has 1,000 grams. But in chemistry, you mostly use grams. We can also measure volume, so we can either use cubic centimeters or a bigger unit called cubic decimeters. So 1 centimeter cubed is 0.001 of a decimeter. Here we asked to convert 23.75 cubic centimeters into cubic decimeters. That's quite easy. We simply divide this number by 1,000 because there are 1,000 cubic centimeters in 1 cubic decimeter, and we get 0.02375 cubic decimeters. So that's a conversion you'll have to do a lot when you're working with concentrations, because in the question you might be given a certain volume in cubic centimeters, but when we're using the formula for calculating, it has to be in decimeters cubed. So just bear that in mind. Another very useful term that we use in chemistry is called the mole, abbreviated as MOL. And it is the amount of substance containing the Avogadro number of atoms, molecules, or groups of ions. And the Avogadro constant is equal to 6.02 times 10 to the 23. You don't have to learn this number, you'd always be given it in the exam. But we use this number because it's exactly the number of carbon atoms in 12 grams of a carbon-12 isotope. So that's quite a good reference point. So 1 mole of any substance equals the relative molecular mass in grams, and the molar mass of a substance is the mass of 1 mole of that substance. So for example, 1 mole of sodium is 23 grams, and so the molar mass is 23 grams per mole. The same goes for a compound. So for example, water, 1 mole of H2O is 18 grams because 16 is oxygen and we have 2 hydrogens, so it's 2 times 1. 16 plus 2 is 18, so that's how much 1 mole of water weighs. Some conversions. There's two ways to remember this. So you can either use the triangle. So for example, if you want to find out the moles, you cover up the moles, and you can see that in order to get the moles you need to divide mass by molar mass. Or if you need to find the mass, you cover it up and you can see that you need to multiply moles by molar mass. Or you can just learn all these, it depends what you prefer. But just make sure you learn this because in chemistry you'll be using this on a daily basis. So let's just quickly look at some questions which are from page 56 and 57. I'll do a couple and the rest you can do yourself. So first of all, question 1, calculate the moles of iron in 1.23 grams. So we need to find the moles. So from here we can see that to get the moles we need to divide mass by molar mass. Therefore, the mass is 1.23 grams. And the molar mass of iron is, if we look at the periodic table, it says that it is 56. So when we divide that, we get 0.0220 mole. Question 2, calculate the moles of water in 4.56 grams. So we've got 4.56 grams divided by the molar mass of water. So we have, and water is written as H2O. So to get the molar mass is 16, which is for oxygen, plus 1 times 2, which is because we've got 2 hydrogens. And that is written as G mole minus 1. So when we divide those, we get 0.253. Also, to double check your units, you can see we've got grams at the top and at the bottom. If we cancel, because they cancel each other out, we only have moles left. That just confirms the units. So let's do maybe question 4. It says calculate the mass of 0.0222 moles of sodium hydroxide, and we're given the molar mass of 40. So how would we do that? So to calculate the mass, we need to multiply moles, which is 0.0222, times the molar mass, which we already given, which is 40. So the mass we get is 0.888 grams. And the last one, calculate the mass of 0.0333 moles of sulfuric acid. So again, to calculate the mass, we need to multiply moles by the MR. In this case, we're not given the molar mass, so we need to calculate that. So we've got 2 hydrogens, so 2 times 1 is 2, plus sulfur is 32, plus we have 4 oxygens. So that would give us the molar mass, which is 98.1. And in order to get the mass, we need to multiply the molar mass by moles, which is 0.033 and so on. And the mass we get is 3.27 grams. So we sometimes may be asked to calculate the number of molecules, and this is quite simple. We simply multiply moles by the Avogadro constant. So for example, in question, for example, the number of H2O molecules in 1.44 moles, in order to get the number of the molecules, we would multiply moles that we are given here by the Avogadro number, which is this one, 6.02 times 10 to the 23. So we get 8.67 times 10 to the 23 molecules of water in 1.44 moles. Okay, so let's do 2 questions. Question number 1, calculate the number of molecules in 3.33 grams of methane. Okay, so in this case we are given grams. So first we need to convert the mass into moles. So to get moles, we need to do mass divided, so 3.33 grams divided by the MR, which we're given here as 16. So we get 0.208 moles of methane. So then to calculate the number of molecules, so number of molecules, we need to multiply the moles by the Avogadro number, which is 6.02 times 10 to the 23, and we get 1.25 times 10 to the 23. Okay, question 2, calculate the number of sodium ions in 2.22 grams of sodium sulfate. And we're given the molar mass of sodium sulfate. So first of all, we need to calculate the moles of sodium sulfate. So to get the moles, we need to divide the grams, so 2.22 divided by the molar mass, which is 142.1. We get 0.0156 moles. But it's asking us to calculate the number of sodium ions and not the number of sodium sulfate molecules. So how do we do that? Well, we still do the second stage as normal. So we multiply the moles by the Avogadro number, which is 6.02 times 10 to the 23. And we get 9.39 times 10 to the 21. So now to calculate the number of sodium ions, because we have, if we look at this here, we've got Na2SO4, because there are 2 sodiums, so we simply need to multiply this number by 2. So 9.39 times 10 to the 21 times 2 gives us 1.88 times 10 to the 22. And that is because each sodium sulfate ion group contains 2 sodium ions and 1 SO4 minus ion. So if this, when this breaks up in water, this becomes Na plus and SO4 minus. But because this is 2 minus, we need 2 sodiums to make this molecule, therefore we need to multiply this number by 2. Mass and volume calculations. So a typical question would involve mass-to-mass calculations, is to ask for the mass of a product that could be obtained from a given mass of one reactant. So, for example, in this case, we are asked to calculate the mass of barium sulfate. So it's always good to underline when you're doing a question. So we're looking at barium sulfate, question mark, and we're looking at the mass. We're asking to find out the mass. That is precipitated, so we know that this will be solid. When a solution containing 5.5 grams of barium chloride is reacted with excess magnesium sulfate. Okay. So first of all, there are 4 steps that we need to follow in this type of question. So in step 1, we need to first write a balanced equation. So we know that barium sulfate is the product, so we can start off with all the things that we know. So BaSO4, and because barium is in group 2, it means it's 2 plus, and we know that SO4 is 2 minus, so it's just 1 barium and 1 sulfate. So, and that is a solid. And we also, so that is the product, and we know when a solution containing barium chloride, so we have BaCl, Cl2 because Cl is minus 1 and Ba is 2 plus, therefore we need 2 chlorines, and that is aqueous because it is a solution, plus is reacted with excess magnesium sulfate, so MgSO4. So again, and that's aqueous as well, and magnesium chloride, which will be aqueous. So once we've looked, we can see we've got 1 barium here, 1 here, we have chlorines 2, Mg, so it's balanced. So that is our first equation that we will be using in this calculation. So step 2, we need to calculate the moles of the reactant. So what do we know? We know that we have 5 grams of barium chloride, and we know the molar mass of barium chloride, so we can work out the moles of barium chloride. So moles is the mass, so 5.55 divided by 208.3, so we get 0.026664 moles of BaCl. So step 3, use the stoichiometry of the equation to get the moles of the product. And what that means is we're simply looking at the ratio of the reactants and the products. Because this equation doesn't have any coefficients, we can see that when we don't write 1 usually, but we can do that here. So when 1 mole of barium chloride is reacting with magnesium sulfate, we produce also 1 mole of barium sulfate. Therefore, because the ratio is 1 to 1, we can also then say that means that the moles will be the same. Therefore, it's 0.02664 mole of BaSO4, which is the product in this case, and that's we're trying to find out the mass. So then step 4, we first need to So in order to get the mass, again using the triangle from the previous page, we need to multiply moles by the molar mass. So the moles of barium sulfate we already know, which is 0.02664, and to multiply that by the molar mass. So to get the molar mass of barium is 137, and there's only one, so 137 plus. Sulfur we have also 1, so plus 32, but we have 4 oxygens, so it's 4 times 16. So moles times the MR, we get 6.22 grams of barium sulfate. So that's how you would do this type of calculation. Let's look at another example. In this case, the question is asking us to calculate the mass. Again, it's always useful to underline things. The mass, so that is what we don't know, of sodium sulfate, which is the product, produced when 3.45 grams of sodium hydroxide is neutralized by dilute sulfuric acid. Okay, and this time we are given a balanced equation as here. So we know, you can always write, so we know that we've got 3.45 grams of sodium hydroxide. We know that the acid is in excess, which means we don't need to worry about that. It's just when we say it's in excess, it's to make sure that everything is neutralized. And we're asked to find out the mass of sodium sulfate. So grams, we don't know. Okay, so first of all, calculate the moles of the reactant. So we know how many grams of sodium hydroxide we have. So we can calculate the moles of sodium hydroxide. So mass is 3.45 divided by molar mass. So for sodium, we've got, for sodium it's 23, plus 1 oxygen, which is 16, plus 1 hydrogen. So we get 0.08625 moles of sodium hydroxide, which is our reactant as shown here. So then, step 2, we need to use the stoichiometry of the equation to get the moles of the product. So in the previous example, we had a 1-to-1 ratio, but in this case, we can see it's not. So we can write it out. So we have 2 moles of NaOH, and the product that we're interested in is the sodium sulfate, as shown here, and there's only 1. So it's a different ratio now. So we've got 2 moles of sodium hydroxide producing 1 mole of sodium sulfate. Therefore, the relationship is slightly changed. So in order to get the moles of sodium hydroxide, we need to divide 0.08625 by 2, which is of sodium sulfate. You convert the moles of product to mass. So we now have the moles. So to get the mass, we multiply moles, which is 0.043125 by the molar mass of Na2SO4, which is, so we've got 2 sodiums, which is 23 times 2, plus we've got sulfur, which is 32, and we have 4 oxygens. So when we multiply all of that, we get 6.13 grams. So let's talk about volume of gas calculations. So that's a different triangle we use. So we've still got moles here, but now we have the volume in decimeters cubed instead of the mass. And instead of molar mass, we have molar volume. So the molar volume of a gas is the volume occupied by 1 mole of that gas under specified conditions. So the pressure and temperature will have to be specified. And generally, 24 cubic decimeters per mole is equal to 24,000 cubic centimeters per mole. And we will always be given a molar volume, because that will differ depending on pressure and temperature conditions we have. So let's look at this question here. Calculate the volume of CO2 produced when 2.68 grams of calcium carbonate is heated and decomposes. We're given the molar volume, which is here, and we're also given the balanced equation. So step 1, we need to calculate the number of moles of calcium carbonate, because we know the mass, which is 2.68. So first of all, let's work out the molar mass of calcium carbonate, which is this one here. So Mr is, calcium is 40, plus we have 1 carbon, which is 12, plus we have 3 oxygens, so it's 3 times 16, which when added up together gives us 100.1 grams per mole. So to get the moles, we can use the previous triangle, in which one we divide the mass, which is 2.68 grams, by 100.1, which gives us 0.0268 moles. And we are trying to find out the volume of carbon dioxide produced, which is here. So we can then use the stoichiometry. So in this case, we can see that the ratio of carbon dioxide and calcium carbonate is 1:1. Therefore, the moles of CO2, which is the one we're looking at, is the same as that. So then the final step is to convert the moles into a volume. So we can use the triangle here. So if we cover up volume, it says to get volume we need to multiply moles by the molar volume. So to get the volume, we need to multiply this number, which is the moles, 0.0268 times, and we are given the molar volume here, which is 24,000 centimeters cubed. And it will be useful to write in the units so we know what the final unit will be in. So when we multiply those two values, we get 643, and this one, sorry, is mole 1. So the moles cancel each other out, and we get 643 cubic centimeters of carbon dioxide. Okay. We also need to know about concentration. And this is the final triangle that we need to know. So we've got concentration at the bottom, moles and volume. So first of all, concentrations apply to solutions. So a solution contains a solute and a solvent. The solute is the substance that is being dissolved. So for example, table salt. And a solvent would be the substance that is doing the dissolving. So that would be the water. So if you wanted to dissolve salt in water, that would be an example. So solutions can be colored or colorless, but they're always clear and never cloudy. So we also need to be familiar with the units of concentrations, because solutions can contain different amounts of solute. The most common unit of concentrations is moles per decimeter cubed, and it's sometimes given a symbol M, which is molarity. So you can sometimes see that written on acids and things like that. And to calculate the concentration in mole per decimeter cubed, the amount moles of solute is divided by the volume of the solution. So let's look at this question here. It says A, calculate the concentration in mole per decimeter cubed of solution made by dissolving 0.123 mole of sodium hydroxide in water and then making up the solution to a total volume of 250. So first we need to work out the volume of the solution. And remember, I said before we need to sometimes convert the units. So because in this case we have 250 cubic centimeters, but in order to use this triangle, I should have written on there, we need to use decimeters. So therefore we need to divide 250 by 1000, which gives us 0.250 cubic decimeters. So that is the volume of the solution. And then we can find out the concentration by using the triangle. So the concentration is moles divided by the volume. And the moles we're given here, and we now have the volume in the correct units. So 0.123 mole, I'll keep the units just so we can see how they cancel out, divided by 0.250 decimeters cubed, which gives us 0.492, and these don't cancel out, so it's moles per decimeter. We have to put -3 because it is at the bottom of this. So that's our concentration that we worked out. And part B is asking us to calculate the concentration in grams per decimeter, and that's quite easy. We simply need to multiply the concentration by the molar mass. So molar mass of NaOH, so we have sodium, which is 23, plus we've got one oxygen, which is 16, and one hydrogen. That gives us 40. So we need to multiply 40, which is the molar mass, by the concentration, which is 0.492, which gives us 119.7, and the units we're given here are grams per decimeter. Other things we need to be aware of are percentage yield calculations and atom economy. So sometimes we may be asked to calculate the percentage yield, and to do that we take the actual yield, divide that by the theoretical yield times 100. So the actual yield is the mass of the product that we obtain from the experiment, and the theoretical yield is what we calculate from the chemical equation. So here is an example. In this question we have 1000 grams of sulfur dioxide which reacts with excess oxygen, and it produces 1225 grams of sulfur trioxide. Here is the equation, and we're asked to calculate the percentage yield. So the first step would be to calculate the theoretical yield of sulfur dioxide, because we are given the grams of it. So to do that we add sulfur, which is 32, plus got 2 oxygens, so 16 times 2 gives us 64.1. That is the molar mass. So then we need to first get the moles of the sulfur dioxide. To do that we divide the mass, which is 1000 grams, by the molar mass, which is 64.1. So the moles we get is 15.6 moles. So then we look at the equation, so we can see that the relationship is 2 to 2, so it's the same as 1 to 1. Therefore the moles of sulfur trioxide, which is SO3, is that, which is the same as the moles of sulfur dioxide. So, and then in step, this is our actual yield. So now we need the theoretical yield. So to do that, we multiply the MR by number of moles, which gives us 1,250 grams. And then in order to get the percentage yield, we do actual yield, which is 1,225 grams. We divide that by the theoretical, which is 1,250, and we multiply that all by 100, in which case we get 98.0%. So that is our percentage yield for this question. Let's also look at atom economy. So in order to calculate percentage atom economy, we need to divide the mass of the useful products by the mass of all reactants times 100. So here I've got an example. It says, what is the percentage atom economy for the following reaction where iron is the desired product, assuming the reaction goes to completion? So on top we need the mass of the useful product, so which we're told is iron, and we have, according to the equation, we have 2 irons, so then we multiply it by 2 and divide it by the mass of all reactants, so that's the RAM, and multiply that by 100, and we get 4, which is the percentage atom economy. And finally, I thought we would conclude at looking at the confirmation of equations. So if the masses of both reactants are known, the stoichiometry of the equation can be worked out. And this is done by converting the masses of amounts and examining the ratio of these amounts. So here I've got a question. It says we have 3.48 grams of pure iron, which was placed in excess copper 2 sulfate solution and stirred until all reaction had ceased. The residue of copper was filtered off, washed and dried. It had a mass of 3.95 grams. Use these data to work out which of the 2 reactions below took place. And we're given 2 equations, equation 1 and equation 2. So first of all, we need to calculate the amount of iron that reacted. So in order to do that, we need to divide the mass, which is, so let me just write the mass straight away, 3.48 grams divided by the molar mass, which is 55.8 for iron, if you look at the periodic table, which gives us 0.0624 moles. Then we also need to calculate the amount of copper produced. So again, we are told what the mass of the copper is, which is 3.95. And the molar mass of copper is 63.5, so we divide that by 63.5 and we get 0.622 moles. So within the experimental error, these numbers are in the ratio of 1 to 1. So the ratio is 1 to 1. Therefore equation 1 is correct, and that's because we have 1 iron here and 1 copper here, and they're in a 1 to 1 to 1 ratio. Whereas in equation 2, we have a ratio of 2 iron to 3 copper. And the calculation just carried out does not confirm this. Thank you for listening.